For a long time, multivariate statistics suffered from the fact that there were simply not enough mathematically manageable multivariate distributions to work with. We have already mentioned this in an earlier video. This problem has now gone away to a great extent due to the discovery of copulas. In this and the next few videos, however, we shall focus on the standard multivariate distributions that were used before the advent of copulas. These are basically direct generalizations of univariate distributions. Here is a list of all the multivariate distributions we shall discuss. First, multivariate hypergeometric, which is a generalization of our familiar hypergeometric distribution. Then we have multinomial, which is a generalization of binomial distribution. Multivariate normal, obviously generalization of univariate normal, and Wishart distribution, which is a generalization of chi-square distribution. Let's discuss multivariate hypergeometric distribution first. We start with a population of individuals, say all the students in a college. Let the population size be n, that is the number of points that you see here, that is n. These students are partitioned by the value of some categorical variables like blood group A, B, and O, or maybe gender, male and female, or COVID vaccination status, not vaccinated, vaccinated once, vaccinated with a booster dose. In our example, we have shown the categories using colors. There are three different colors here, red, green, and blue. In general, let the number of categories be P. Here, P is equal to 3. Suppose that out of the n students, ni belongs to the ith category. For example, here we have 1, 2, 3, 4, 5, 6 red points. So if red denotes the first category, then we have n1 equal to 6. Similarly for the other two categories. Now we draw an SRSWOR of size n from the population. SRSWOR means simple random sample without replacement. All the points inside this ring that I have drawn are in our sample. So here n is 1, 2, 3, 4, 5, 6 and 7. So little n is 7. Now we count the number xi of students in our sample belonging to category I. For example, here x1 is the number of red points in the sample, which is, I think, is 2. And if we look at number of green points, that is 0, so x2 is 0. So number of blue points, that is equal to 5. Remember that these numbers must add up to the sample size, which is n. Remember that the xi's are actually 3 random variables. We may pack them into a random vector. In general, there are p categories. Accordingly, we have x1, x2 up to xp. This is a random vector whose distribution is completely determined by the capital Ni's and sample size little n. This distribution is called multivariate hypergeometric with these as the parameters. This abbreviation is something that I have just cooked up, which is not standard. Here is the PMF of this distribution. Looks pretty complicated, huh? Let's digest this PMF slowly. This term is the number of ways to pick x1 individuals from the n1 individuals belonging to category 1. The term downstairs is similarly the total number of possible samples of size n drawn without replacement from the population. This sum is actually the population size. Thus, the denominator is the total number of possible samples, while the numerator is the number of those samples that has exactly xi individuals from category I for all I. Remember that the xi's must add up to little n. Also, each xi must be a non-negative integer less than or equal to corresponding capital Ni. If these conditions are not met, then the PMF is just 0. Now, a PMF is a nice, precise way to specify a discrete distribution, but not the most intuitive way to have a feel about a distribution. A better way for that is to be able to simulate from the distribution. That is, carry out a random experiment such that the outcome has that distribution. Let's do that using R in the next video.